Okay, I think that's it for logistics stuff for now. We are going to jump back into talking about diodes. And I'm going to use an analogy that somebody came up at the end of lecture last time, and I think this actually helps hopefully conceptually explain what diodes are doing a little more. So, water analogy again, but instead of a pipe, my pen stopped working, that'd be bad. There we go. Instead of a pipe, just think of it like a dam, right? With a certain height, where height is analogous to voltage here, so call that like the threshold height. So if I start kind of piling up water on the left side of this dam, right? There's nothing flowing over the top yet. And I kind of keep adding water, and keep adding water, until I finally reach that threshold height, and then the water starts flowing over, right? But if I try to keep increasing the height on the left, I can't. Okay, I keep trying to add more and more water over here, but it's just going to reach the top of the dam and spill over. Okay, so I think, I talked about this with the check valve analogy and said, okay, there's kind of a certain amount of pressure that's required before that valve will open. This is at least more intuitive to me. And again, if you're thinking about height as voltage, and there if I ask what's the voltage drop or the height drop across the dam, right? Well, okay, when the diode is conducting or when the water's flowing, right, then it's just the height of the dam. But when it's not all the way filled, say if the water level is still right there, right, sorry about my scribbles here, then that I still have a voltage drop or a height drop over the dam, but there's no current flowing. Okay, so I find that explanation actually more intuitive than the kind of check valve pipe explanation, whichever one works for you. Again, you always have to be careful with fluid analogies because electrons are not literally moving around like water, right? I think one example I've seen where people kind of take the fluid analogy too far is, okay, if you have a pipe with water flowing, then, more water, and there's a T connection like this, then, because of momentum, more water is going to go that way than making the right turn, right? Like, that's not how electrons work, right? Like, if you have wires in a circuit represented by a junction like this, that doesn't mean that, like, more electrons are going to go straight through the wire because they're going to have a hard time turning or something. So again, be careful with the fluid analogy. Don't take it super literally, but I think that helps for diodes. So before we get into more diode math and applications, and again, I sketched from last time, this is all related to that IV diagram where we said, okay, not even worried about kind of the reverse voltage breakdown part, right? We have this really steep graph where the current is almost nothing for a while and then it shoots off to be really high, right? So like here I'm building up voltage, building up height, current is nothing until I finally spill over the top and then the current or flow shoots up. So I hope that helps explain this a little better because I think people were confused about it last time. But conceptual questions about how diodes work. Okay. Then, getting back into a handful of diode applications. The big one is LEDs. Right? I grew up in the age of incandescent light bulbs, but LEDs are all around us now. You got an LED in the flashlight on your phone. You got little blinky LED power lights on your computer. The lighting in this room is probably LED by now, maybe fluorescent. Like there's a little LED right there, and that thing. LEDs are everywhere, right? And an LED. And I said this last time, means light-emitting diode. So it's just a diode that also happens to emit light. Because of physics, we're not talking about, again, with electron energy levels and when it drops down one, it emits a photon while it's at it. Not worried about the physics in this class. But they're kind of a good example or application of diode math. So light-emitting diode. The symbol is very similar to what we've already seen for regular diodes, except there's two little arrows coming off of it like that to kind of represent light coming out. Shape of the IV diagram is going to be the same. The difference is that that forward voltage drop is usually higher. So we talked about how for silicon diodes last time, that voltage drop is around 0.7. For LEDs, it's usually more in the range of 2 volts to 4 volts. And those voltages kind of correspond to the colors of the rainbow, where red is on the lower end of the spectrum and blue is on the higher end of the spectrum. So, I'm going to get this backwards in my head. Higher frequencies, higher energy requires more voltage for the higher frequency, shorter wavelength light. Again, we're not worried about the physics. Point being, the voltages are a little higher, but when you want to control an LED with a battery, right? So you have your Arduino, you can, if you want to put a bunch of little decorative LEDs on your robot at the end of the semester, you can. You did this in lab 2 where you had the breadboard with the LEDs. People's first instinct is to look at that and go, okay, so I have an LED that has a 3-volt forward voltage drop. Why don't I just hook it directly up to a 3-volt battery like this? Say I have a green LED where the forward voltage drop of the LED is 3 volts. Why don't I just do that and connect it directly to a 3-volt power supply, and then I'm fine, my LED lights up? 2 reasons you don't do that. 1, batteries only come in fixed voltages, right? So everything does not have there's the variable benchtop power supplies in lab where you can turn a knob and get exactly the voltage you want. We've seen the AA batteries are 1.5 volts, right? So if I only have AA batteries, then I can go 1.5 volts, 3 volts, 4.5 volts, and so on. But what if I have an LED with a 2.4 volt forward voltage drop, right? I don't have a combination of batteries that will give me that voltage. Second reason you can't just do that is, remember, this graph, that current goes off really, really steeply. So what happens if your battery voltage is actually accidentally like 1/10 of a volt higher than you thought it was going to be? You blow your LED up because you're shooting off on a really high current part of that graph. Okay, so in reality, when we're using an LED in a circuit, you always have what's called a current limiting resistor. Resistor in series with the LED. And this is, again, what you had. That's why those resistors were there in lab 2. Okay, they are limiting the current and preventing the LED from blowing up because you just connected it directly to the battery. Okay, this is a pretty simple circuit to analyze, knowing stuff you already know, just pretty much Ohm's law. So if we have a battery voltage, we'll call that VB, and you know your LED voltage, say VF, the forward voltage over the LED. If you go look at an LED datasheet, there will be a maximum rated current for the LED. So 20 milliamps is common for the little kind of LEDs you used in lab 2. Okay, so I can look at this and say, okay, I know the battery voltage. I know the forward voltage drop over the LED I have, VF, and I have some desired current for the LED. Okay, what should my current limiting resistor value be? What value of R do I pick to make sure I don't blow up my LED? We have a resistor. Ohm's law still applies to resistors, right? Even though this circuit has a diode in it, Ohm's law doesn't apply to the diode. It does still apply to the resistor. And so just like we saw before with op amps, when we started sticking resistors on there, right, we can still apply Ohm's law to the resistors. I can look at this resistor and say, okay, what is the current I to that resistor? I know the resistor is in series with the LED, so that has to be the same as the current through the LED. And I can apply Ohm's law to that resistor by looking at the voltage drop across it, right? So I know this end of the resistor is connected to the battery, so the voltage there, this has to be VB. This end is connected to the top end of the LED. So if the LED is conducting, if I am in that part of the graph, then I know the forward voltage drop across the LED is approximately constant, right? So there, I just have to have VF. So Ohm's law across that resistor gives the battery voltage minus the forward drop across the LED. Okay, remember, we're talking voltage drop across the resistor, not what is this point relative to ground or what is this point relative to ground. Just equals IR. Okay, so depending on how the problem is formulated, right, I could say, I know that I want 20 milliamps through the LED. What should the resistor value be? Or I could say, I used a 220 ohm resistor. What's the current through the LED? Right? It's just one equation, and it depends on what your knowns or unknowns are. Question, and I don't have this set up for a poll everywhere. I'm just going to draw it. Can I do that? Can I put the resistor after the LED, yes or no? Let's see, so nod your head for yes. Shake your head for no. Okay. Or just leave your head still if you don't have an opinion or don't want to offer it. Okay, I'm glad I saw a lot of head nodding for yes. This is okay. And this is a really common misconception. People think, wait, you have to somehow drop the voltage or drop the current to protect the LED, so the resistor has to be first. That is not true, right? They are both still in series here. So the current through them is still the same. Okay, in this case, the voltage drop across the resistor. Again, here I'm going to have the battery voltage VB. Here, I'm going to have the battery voltage VB minus the forward drop across the LED. And then that's the remaining voltage. So that doesn't change the calculation, basically. It's not, the resistor is not somehow reducing the current or dropping the voltage before it gets to the LED. What matters is the drop over each component. Okay, so that's I have a YouTube tutorial about this, and that's like the most common. Actually, sorry, it's on a breadboard tutorial where maybe I draw the circuit diagram like this, but then when I actually build the circuit, I put the resistor after the LED, and people ask like, "Hey, wait a minute, can't you do that? Doesn't the resistor need to be first?" So it doesn't really matter whether the resistor is before or after the LED; it works the same. What gets interesting, and I ran out of space on this paper, so I'm going to go to the next one, is if you have multiple LEDs, how do you wire up multiple LEDs? And that's going to depend on your battery voltage and the forward voltage drop of the LEDs. So the kind of simplest thing to do is just to put them all in parallel, each with their own current limiting resistor, like this. Okay, since they're all in parallel, the voltage drop over each branch of the circuit here is the same, right? They all just have that battery voltage VB across them, so you can just do that calculation for each individual branch. And say if you have different color LEDs with different voltage drops, then you can pick a different resistor for each one. But say, for example, I have a 9-volt battery, and I want to do that, but the LEDs only have a voltage drop of maybe about 2 to 4 volts across them. So that means I'm dropping 5 to 7 volts across the resistor, right? That's a lot of wasted power just across the resistor that's just dissipating it as heat. So you can also just put LEDs in series. Like this, right? So say I had 3 red LEDs with a 2-volt voltage drop across them, right? 2 volts, 2 volts, 2 volts. Well, now, in series, the LEDs are dropping 6 volts, and now I'm only dropping 3 volts across the resistor, right? So compared to, if these were all red LEDs with a 2-volt drop, I would be dropping 7 volts across the resistor. So in this case, the power dissipation by the resistors is way higher than in this case. So the current limiting resistor is kind of a necessary evil where it's always going to dissipate some power, right? It's just dissipating power as heat. It's not converting it to useful light. But this is still way more efficient than incandescent lights. This is kind of a tangent. Right? When we talk about LEDs being more efficient than incandescents, that is because they convert more electrical energy into visible light. Okay? Incandescent lights convert plenty of electrical energy into electromagnetic radiation, but most of it is infrared, so we can't see it. So it is useless to us in terms of illumination, right? So when you hear about LEDs being more efficient, that's why, right? That they are, if you look at, you can look at a spectral graph. This is again kind of a aside. The intensity of different light spectra for incandescents. For incandescents, it looks something like that, where visible is over here, and over here is infrared, so a lot of that energy is just wasted in infrared, and then for LEDs, more of it is over here in visible. So that is why, again, since my childhood was totally incandescent bulbs, and now we've shifted to mostly LED lighting. Okay, so again, is this a mandatory thing you're going to need to do in this course from now on? You'll do a few more exercises with LEDs. If you want to put blinky LEDs on your robot at the end of the semester, you can. This is how you make sure they don't blow up. Okay. LED questions. Yes. Math is that the math. So if these, let me clarify, none of this math would change if these were just regular diodes that didn't emit light. But so mathematically they behave the same. They just also happen to emit light. Question? Yes.
If like the V app is like smaller than its value, so it's just like more light out.
Yeah. So if, for example, if this was if I have a 1.5 volt battery, so a single AA battery, that's just not enough voltage to light up an LED. Right? So that's where, with the dam analogy, you haven't reached the height needed to turn the diode on yet. If the LED has a 2 volt forward voltage drop and your battery is only 1.5 volts, then that's not enough voltage.
So if like a LED can blow up, is because voltage or the current?
It is because there is, so the question was, if an LED can blow up, is it because of the voltage or the current? It is because if the voltage gets too high, then the current skyrockets.
Yeah.
And that generates too much heat and is what causes it to explode. So really, I think, technically it's power, so both voltage and the product of voltage and current that will be converted to heat and will then, it can only dissipate, most, I guess, you're not a MAE, right? You're a different department. You are a MAE? Okay, so you're taking heat transfer right now, right? So the physical plastic package of the LED radiates and has convective cooling, and then the metal leads that are plugged into the breadboard have heat conduction, right? So there is only so much heat that can be dissipated before it literally just overheats and burns out. Okay. Okay. Other LED questions? All right. We are going to talk about several more useful applications of diodes. These, thankfully, don't really have a lot of math. They're just kind of conceptual things. And then if we have time, my device. I just got blue screen of death again, so we will see if my computer decides to restart and do the poll everywheres. If not, then everybody just gets a freebie for today, so we'll see how that goes. All right. Okay, switching topics. I forgot to bring my cell phone charger today. My laptop charger is plugged in over here. But we've talked about these things a couple times before, right? When we were talking about RC filters, and I promised, hey, I would come back to this when we talk about diodes. So again, when you have a thing that plugs into a wall outlet that charges a battery, you need to convert AC, which is a sine wave that's going both positive and negative, to DC, to a flat positive line. So my question, which I was going to do as a poll everywhere, but this is at 0% complete for rebooting, so we'll see how that goes, is what happens if I feed that sine wave into a circuit like this with a diode. So I have a diode there, a resistor R there, and V out there. Okay, and assume that the magnitude of V in is much, much bigger than the diode drop. So maybe I have a 0.7 volt over the diode or something, but this is 120 volts. This is coming from a wall outlet. So we just kind of ignore that tiny drop over the diode. What does V out look like? I'm going to draw 4 different options here. Okay, does it do nothing? Does it just look the same as the input? Does it just keep the positive half of the input and get rid of the negative half? Does it just keep the negative half of the input and get rid of the positive half? Or does it make everything positive? Okay, I need to log back in here and pull up Pull Everywhere again, so start thinking about that. And assuming my computer doesn't crash again, I will launch the poll in a minute. should be activated now. V in is sinusoidal, going positive and negative. I didn't draw it here, but this is reference to ground, right? So V in can be either a positive or negative number. Which one of those graphs represents V out? Alright, I'm going to give this 30 seconds. We got a couple more examples to go through.
So I feel like
25, 20, yeah.
What do you think it is? Okay. That's 2 out of
10, 5, 4, 3, 2, 1. Deactivates. Correct answer, which 84% of you got, good job, is B. Okay. So if you didn't get B, again, don't worry about it. Diodes are not always intuitive. Okay. So think about this one kind of step at a time. If the voltage here is positive, if V in is greater than 0, I'm saying it's a lot bigger than the drop across the diode. Okay, so we're ignoring the part where say, oh, that this diode has a forward voltage drop of only 0.7 and the input voltage is only 0.5, so it's not conducting yet. We're just ignoring that. We're saying the input voltage is 120. Okay, so that's going to be enough to forward bias the diode. The diode's going to conduct, but there's pretty negligible drop over it, so the voltage here is also going to be positive, right? So I'm keeping for the positive part of the wave, the output's just going to look like the input. But, so in that case, I have current, and the resistor or the load pretty much gets the full input voltage. If the voltage here is negative relative to ground, then that is when the diode blocks reverse current. Right, so no current. There is no backwards current. That current has to be 0 because the diode again works like a one-way valve. It doesn't let current flow that way. As we have seen like a dozen different times now, if the current through that resistor is 0, the voltage drop across that resistor must be 0. Right? So if the voltage there is 0, it's tied to ground. Voltage there must also be 0. So that is where you get this. For the negative parts of the input, the output voltage is just 0. So this circuit is called a half-wave rectifier because it hasn't made everything positive, but at least in terms of charging a battery, I have gotten rid of the negative parts, right? So I wouldn't be charging and discharging my battery. I would at least be charging it, but I can probably do better than that. Right? Again, ideally, we want to go from a sine wave to a perfectly flat line. So, next circuit, I'm going to try and slide that up to leave room and draw the next one. This one gets a little more confusing to draw. Give myself a second to make sure I do this right. I'm going to have 4 diodes now. No cheating if you took another circuits class and saw this before or something. Don't spoil it for everybody else. Do this right. I messed up drawing my diamond, but you get the idea. That connects there. So again, V in is V in, that didn't quite fit. V in is sinusoidal again, going positive and negative, referenced to ground down here. V out is now the voltage drop over this resistor. Okay? Again, same question, what does the output look like? Does it just look like the input? Does it look like just the positive part of the input? Does it look like just the negative part of the input? Or does it look like that? Okay, kind of making everything positive. So let me, and you may just kind of be able to guess at this based on where we were going, but I kind of want to work through the reasoning. So that is active. V in is a sinusoid. What does V out look like if I graph it? Assuming, again, V in is just, I draw the graph, 2 periods, positive and negative. Yes?
Where's the out being measured?
Across this resistor. So V out is the voltage drop across this resistor with this sign convention. This side's positive, that side's negative. So note that that is not referenced to ground, right? So in the previous version, it was just implied V out was relative to ground. Here, V out is the drop across that resistor. Yes?
I think I might have a silly misconception, but can voltage travel either direction on an LED?
So voltage doesn't travel, right? I don't think that's the right way to formulate that. Current can only travel in one direction. Okay. You can have, so if we draw, this is kind of an aside to answer your question, the full IV graph for a diode, we were just kind of talking about the positive part here. You can have a reverse voltage across it, but there will be no current until that voltage gets so huge that it blows the thing up. Again, kind of think of like pressure breaking backwards through a check valve. Right?
So there's effectively none?
There is voltage, there is no current. Right? Does that make sense? Yeah, so that in reality, there is like a small leakage current in like the nanoamp or picoamp range, but for purposes of the simplified mathematical model, it's just 0.
Either.
I didn't realize I didn't turn my mic back on, sorry.
0 for...
0 current. Okay, y-axis here is current. I can have a reverse voltage across a diode, just like you could have, if you have 2 pressure taps on both sides of the check valve, right? You can have a pressure difference in either direction. The pressure can be higher on one side or higher on the other side, but you can only have current in one direction. Make sense?
Yes. Thank you.
Yep. All right. I want to keep going, so I'm going to give that 10 seconds. 5, 4, 3, 2, 1. Deactivate. Correct answer. Ooh, we're a little more divided on this one. So a lot of people said A doesn't change the input, but the majority of you said D, which is the correct answer. So this is called a full wave rectifier. Now I'll explain why it is not A in a second. So called a full wave rectifier because now instead of just rectifying half the wave, rectifying meaning making positive, we're rectifying the whole wave, right? We're getting rid of the not only are we getting rid of the negative parts and making them 0, we're actually flipping it and making the whole thing positive. So to think about why that works, remember that ground is 0 volts. So when V in is positive, right? When I have a positive voltage up here, Okay, current is going to flow forward through the diodes that are forward biased, have a higher positive voltage on the positive side than the other, right? So at this junction, if this is positive, okay, current can't go through that one because that's backwards, right? So current can go this way. I get to this junction, current cannot go through this diode because that one's backwards, so it can go through the resistor. And then here, it's not going to flow back, like both of these diodes are pointing away, but it's not going to flow back up to positive voltage, right? It's going to keep flowing towards the more negative voltage, so current's going to go down there. Okay, is that clear? Which zigzaggy path current takes through this circuit when the input voltage is positive? Because I think that is the, if not more intuitive, less unintuitive of the two options. Okay. I'm saying, so like, if you don't understand this, then the next one's not going to make sense either. So does that make sense?
Yes.
Okay. So if the voltage up here is negative, okay, current's going to flow. Remember, this stayed at 0. Okay, so that is now lower than 0. Current is going to flow the other way. Okay, so current goes this way. At this junction, I can't go through that diode because that one's facing the wrong way. Right? I can go up through this diode. Now this is the key part. I can't go through that diode, so it goes through the resistor in the same direction. Okay, the direction of the current across the resistor did not change. So the sign of the voltage drop across that resistor also does not change. Okay, so I get to here, and then again I'm going towards the more negative voltage. I'm going to go up there. Okay, so regardless of whether the input voltage is positive or negative, the direction of current through the resistor always stays the same. Okay, if the direction of current through the resistor was flipping each time, then A would be right. Right, the voltage drop as measured. If you had a multimeter hooked up with a positive lead in one place and a negative lead in the other place, then that voltage would actually be changing positive and negative. Okay, but the way I'm measuring it here, positive on this side, negative on that side, that voltage is always positive. So it's like taking the absolute value of A. Okay? So that is how, there's then one more step that we talked about earlier, right? We want to charge a battery. Ideally, we'd like that to be a nice constant value and not this kind of half sine wave value. You take the output of this circuit and feed it into a low-pass filter. Right? So remember our RC circuit where we said, okay, if we drive that with a square wave on the input, then the output, it kind of takes a while for the capacitor to charge up, and then it takes a while for the capacitor to discharge. Well, think about that here. If this is the input to this circuit, then okay, the capacitor is going to charge up. But then when the input goes down, it takes a while for the capacitor to discharge because there's a time constant, right? And then it hasn't discharged all the way, and then it starts charging it back up again. And then it takes a while for the capacitor to discharge because there's a time constant, and so on. So again, I forget which lecture we talked about this in. It's not a perfectly flat line. There's something called a ripple voltage. Okay, so it's oscillating up and down a little bit, but we have now taken a sinusoidal signal going positive to negative and gotten it pretty close to something that is a flat line. Okay. Are you ever going to need to build a rectifier from scratch as a mechanical engineer? No. Should you know what this means? Yes. Okay, when you hear the word rectification or full wave rectifier or half wave rectifier or something, this is what they're talking about. And again, in practice, when you look at these power supplies, if you zoom way in there, it's going to tell you what the input and output parameters or ranges are, right? Like, if we live in the US, the wall outlets are 120 volts. You go to a different country, sometimes it's 220 or something. So that tells you if you're traveling internationally, whether or not your cell phone charger is going to blow up if you plug it into the wall outlet. And then same for the output and different voltages. Phones charge at USB spec, which is 5 volts. If you have random, I have to zoom in on the laptop one here. This is a laptop charger which outputs 19.5 volts, right? So don't try to use this to charge your phone or it's going to blow up your phone. Okay, so zooming, wing, and that text is kind of blurry, but there's the output there, can output 19.5 volts and up to 2.31 amps, and I'm not going to bother trying to squint to read the input specs on this one, but that's kind of what all that, this is what the circuits in these things are doing. Okay, questions on the full wave rectifier? Does anybody not believe me that the answer is D? Yes?
In our first case, we ended up with B, where we have this sort of dead space between our maximum points.
Yep.
How does this full wave rectifier fill in that so-called dead space?
So that's the blue line here, right? So remember, if the input, if I draw that here, when the input is negative, so when the voltage up there that I drew the minus sign, right, is negative, then current is flowing kind of the opposite zigzag through this circuit, but the direction of current through the resistor did not change. Okay, so the voltage drop over that resistor is still positive. Okay, and my output is the voltage drop across that resistor. So I took this negative input, and the output I'm measuring is the voltage drop over the resistor. So this voltage for that phase of the input is now positive. Compared to the circuit that just had one diode, where when the input voltage was negative, then the output was just 0, right? There's no current through the resistor in this case. So that's the difference between these two cases. Here, when the input voltage is negative, there is no current through the resistor. So the output is 0. Here, when the input voltage is negative, there is still current through the resistor, so the output is not 0. Does that make sense? Okay. If not, I want to get through one more example. If that still doesn't make sense, talk to me after lecture and we'll see if I can explain it better. Okay. All right. Other questions on the full wave rectifier before we squeeze in one more example here? Yes?
Do you think you can explain ripple voltage and low pass filter, like how you got the...
So remember, so the question was, can you explain ripple voltage in the low pass filters? So remember, let me draw this out a little more. Our RC circuit like this. If I sent an input voltage like into that was a square wave, right? And then looked at the output voltage had this time constant behavior where it took a while to charge up and discharge, right? So just imagine if instead the input here was this kind of half sine wave thing, then that's what I drew up here. It's going to charge up, but then when the input goes down, the output is going to decrease slower because of the time constant. That's assuming you've chosen R and C values that are big enough to have a big enough time constant. Right? Like if R and C are too small, then it'll just follow this. But if the time constant is big enough, then it's going to start just that's like this part here, right? When the input before it was a square wave, it didn't follow the square wave. It kind of went down slowly with the time constant. Same thing here. The input isn't a perfect square wave, but that doesn't change that it's going to take time for the voltage to go back down. But then since it then hits this while it's going back up again, then it just charges back up and slowly goes back down. So this now blue line here never has time to get all the way back down to 0 because it keeps hitting the next bump of this. And then the result is that it's not perfectly flat, it's kind of going between these 2 points, and that's your ripple voltage. Does that make sense? Okay. All right, other rectifier questions? All right, one more example of a kind of much more practical diode application and something you might actually need to do when dealing with motors, and I think I should be able to fit this in the last few minutes here, is something called a flyback diode. Okay, so remember inductors, and again this is going to be kind of conceptual without really having any math. Imagine that I have a circuit with an inductor, and I just open a switch at t equals 0, right? And remember, so I had some current flowing through the circuit, and I open the switch. Okay, so I have an open circuit, and current can't be flowing. And I'm going to define my sign convention on my inductor is like that. So positive end here, negative end there. Remember the inductor equation. V equals L di dt. So if I open the switch, if I had a graph of current versus time, and I'm sorry, I should have drawn, there's some tiny non-zero resistance in series with the inductor. Because again, if in steady state an inductor acts like a short circuit, so we would have infinite current in that circuit if there was no resistance. There's a little bit of resistance, but we're not worried about that too much. I say I was just cruising along with some constant current, and then bam, I open the switch, so current has to drop to 0. Okay? The derivative of the current on that graph is negative infinity, right? So if this is negative infinity, then according to this equation, that means the voltage is also going to be negative infinity. So let me draw this with the switch open now. That switch is just opened. The current through the inductor suddenly wants to drop to 0 because the switch is open. Okay, but because of this, I have a huge reverse voltage induced, I think about the name inductor, across the inductor, where now there's this huge, like tens or hundreds of volts reverse voltage induced across the inductor because I tried to stop the current from flowing. And in practice, what's that's going to happen is kind of a spark across the gap. And that current like really wants to keep going. It doesn't want to stop. Again, think of the analogy of an inductor like a mass. This is literally just having like a mass go into a brick wall. Okay, you have a mass that is cruising along at some velocity v, and it crashes into the brick wall, so the velocity suddenly comes to 0. Right? We'll think about F equals MA. Velocity instantly going to 0 is a huge negative derivative on the acceleration, right? Which is going to cause a huge negative force in that direction and either break your mass or your wall. That's kind of the electrical equivalent of that. That spark is going to damage that huge reverse voltage, and that spark is going to damage something. Okay. The way to fix that, okay, well I have a motor that's on. How do I turn my motor off without damaging something? Is with a flyback diode. So we are going to take our circuit and put a diode in the reverse direction across the inductor. Okay, so in normal operation, current's just flowing through that inductor. I don't have any current through the diode because that's the wrong direction. Okay, but let me double check. I don't think I have a pull over for this one. No. When the switch opens, okay, so there, that diode is what we call reverse bias. The voltage across it is in the wrong direction. Okay, so the diode's not going to conduct. Okay, battery voltage is positive there, negative there. That means I have positive there and negative there across the diode. Diode's not going to conduct. All right, we got a few minutes. We're good. But I open the switch. Now that reverse voltage wants to be induced across the inductor. Okay, so now I have positive there and negative there, but now the diode is forward biased. So now that current has somewhere to go. It can go through the diode and just dissipate in that loop until this voltage comes down to 0, rather than jumping across the switch. Okay, so when you see the phrase flyback diode in relation to an inductive load, excuse me, that's what this is talking about. You have a motor or a solenoid or a relay, something that is a coil of wire with a magnetic field. A flyback diode helps you turn it off safely without damaging your equipment. I see you again, 1 second. Sometimes this is an external part. Sometimes it is internal to an integrated circuit, like something called an H-bridge, which we are going to use to control motors next week. But let me pause there for questions.
What is the sign convention on the left bottom left circuit?
So, there is sign convention there. So, sorry, there's a difference between sign convention and then the actual voltage induced. So if this is my sign convention, okay, I'm saying that is the actual voltage over the induction here because it matches the battery, right? Then I can keep that sign convention over here, but with that sign convention, this voltage is going to be a negative number. So I just kind of was lazy about it and drew it the other way. But again, here it's connected to the battery, so the voltage across the inductor has to equal the battery voltage, right? Here, I've disconnected the battery. In ideal math world, that voltage is now negative infinity. In reality, like that derivative isn't perfectly zero infinity, right? But it's some very large negative number, so there's going to be a very large negative voltage there. Okay, and again, I didn't draw, but there's a little bit of resistance in these wires, right? So that current just kind of dissipates. It all gets dissipated as heat instead of instantaneously as a spark that can damage the switch or something else more sensitive in the circuit. Okay, so in terms of things you might actually need to do, not just know about, this is one of them. Okay, if you go do something with a microcontroller to control motors, you need to figure out if the circuit you're using to control the motor has a built-in flyback diode or if you need an external one. So I'm going to jot that down. Can be built in or external. So a year from now, if you're using an Arduino and an internship for a class or your job or whatever, and you're controlling a large motor and you accidentally blow something up, okay, it might be because you forgot the flyback diode. Conception, I realized the first time that this idea of like the diode isn't conducting here and then it is conducting there can be kind of hard to grasp the first time. So again, there's no math here. This is just kind of purely conceptual. Conceptual questions about how the flyback diode works. You all believe me? Yes?
Why should not need a load resistor in this case? The diode is like burning out.
So the question was, why would you not need a load resistor in this case? Won't the diode just burn out? There are diodes designed to handle this. Basically, thermally, they can just handle that very large. The max current is tens of amps or something. And again, in reality, there isn't zero resistance here. The inductor has resistance to it. The wires have resistance, so it's not literally zero resistance.
So it's basically like a directional resistor.
I don't know if I would call it a direct. Well, yeah, I guess you could say that. Okay, thank you everyone. We will start talking about transistors on Monday. I did not get to pre-record a video about transistors yet, so for anybody who wants to get a super early start on next week's homework, there is a PDF on Canvas, but you're going to need to do a little more research on your own if you want to get started on that one. All right? Thank you.